Hvala. I will talk also in English. So this presentation will be about our latest research during the project, and these are results of my PhD student Dragana. She spoke yesterday about extrapolymer substances. I will now go deeper in this. So let's start. I will now talk about some basic information. We use anaerobic digestion technique for reducing waste and producing biogas, turning this waste into energy that can be utilized later, because we are all aware about increased population, and this increase is directly related to the increase of wastewater treatment plants and later on waste amounts of produced sewage sludge. We are aware that sewage sludge contains many toxic substances. It represents odor and hygiene concerns, and its proper treatment is very crucial. So promising fit for purpose technique is definitely anaerobic digestion, because it can stabilize sludge, remove odors and pathogens, reduce the solid mass, and produce biogas. So anaerobic digestion contribution is some estimation that it can mitigate around 100 megatons of CO2 equivalent of greenhouse gases per year, and it's mainly a result of the fossil fuel-based energy replacement. On this picture is represented basic 4 steps of anaerobic digestion process. So we all know about hydrolysis, acidogenesis, and methanogenesis, and we are all aware that sewage sludge is a very complex organic matter that needs to be deteriorated to soluble organic molecules, later on volatile fatty acids, acetic acids, and at the end at methane and CO2. So this sewage sludge is complex flux structure, and it's composed of extracellular polymeric substances, and these hard cell walls obstruct the efficient performance of that process and lead to inadequate methane output. So we need to pre-treat this anaerobic digestion, and there are many technologies and techniques in consideration, and they include physical mechanical treatments, thermal, chemical, biological, and their combinations. This picture, this table, is a brief comparison of various pretreatment technology in terms of investment cost, operational costs, and energy requirements. As we can see, pretreatment technology that have a large investment costs and operational costs are definitely ultrasonication, high pressure homogenization, high temperature pretreatment, and they also have large energy requirements. In comparison to that techniques, chemical pretreatment and biological pretreatment are having much lesser investment and operational cost, and they are they're less energy intensive in comparison to physical, mechanical, and thermal pretreatment, and that's why we decided to use these chemical pretreatment methods to reduce waste and to produce more biogas. Also, chemical reagents increase the overall costs of chemical pretreatment, but on the other hand, they balance these additional costs by reducing waste amounts, and also they are recommended due to good net environmental performance. So the aim of this work is to pretreat waste-activated sludge with green, non-invasive, cost-effective chemicals. Today I will talk about pretreatment with acetic and citric acid, and I will give an information about their impact on EPS and pharmaceuticals degradation. We have planned also to use many other green and non-invasive cost-effective materials in the future, but I will now focus on these two. So the experimental part is next. So we used the standardized biochemical methane production test with 300 milliliters glass serum bottles, and we used an alcohol substrate ratio of 2. Those experiments were performed in anaerobic thermophilic conditions and lasted for 10 days. Besides of many ordinary parameters such as phosphorus and metals and nutrients. We also determined it and followed fast alkalinity and volatile fatty acid analysis by titration methods. Also, the process of extraction of extrapolymeric substances and total content of polysaccharides and proteins were done according to well-known phenylsulfuric acid method and Lowry method, and the analysis was done spectrophotometrically. Targeted and non-targeted analysis was performed by our colleagues from UPEC last year in June, and they helped us with this investigation. Data modeling was done using the Gompertz mathematical model. So we used this mathematical model to describe and compare quantitatively the experimental data on the methane production. We used Excel solver function to estimate 3 different parameters by fitting the experimental data and the theoretical model using minimum square error methodology. The parameters that we used were maximum specific methane production, maximum methane production rate, and lag phase. Concerning target and non-target screening, this would be a scheme of that extraction methods by Quechers and SP purification. As you can see, it starts with 1 gram of freeze drying solid of sludge, and there's addition of different salts and different solvents. There is a lot of water-testing and shaking and mixing, etc. And after that, we're going to do the SP extraction with homemade cartridges, and later on was performed target and non-target screening. Concerning results, here are the presented pretreatment of acetic acid of anaerobically digested sludge. So these are experimental and model results on this graph presented, and the measured parameter that I mentioned earlier. So based on the graph, we can conclude that maximum specific methane production increased with increased acetic acid concentration from 28% to nearly 250% compared to control. Concerning maximum methane production rate, it also has a positive impact, showing significant statistical differences at higher concentration of acetic acid. It has 2 or 3 times higher values compared to control. Also, the lag phase showed slightly significant statistical difference with addition of acetic acid. So we can say that approximately there is no any statistical difference concerning lag phase. When we come to citric acid pretreatment, it showed that maximum specific methane production is lower in comparison to acetic acid pretreatment, and it is in the range of 20 to 150%. Also, the maximum methane production rate has 2 or 3 times higher compared to control, and with increase of acetic acid concentration, and also lag phase didn't change significantly. Concerning EPS extraction, we have three fractions that there are soluble bound EPS, loosely bound EPS, and tightly bound EPS. So based on this applied treatment with acetic acid, firstly from 1 to 5 millimoles concentration, we can see that there's practically we cannot correlate the amount of acetic acid with the polysaccharide and protein content in the Epps fraction. We can say that increase in acetic acid quantity resulted in higher polysaccharide content in solubly bound Epps. However, the loosely bound Epps has 3 times less polysaccharide when treated with the maximum acetic acid, whereas during the same treatment condition, extreme polysaccharide release was noticed in the tightly bound Epps. So concerning protein content, we can generally make conclusion that reduced protein content was obtained during this treatment. Exception exists in fractions such as soluble bound and loosely bound Epps when the highest and the lowest acetic acid concentration was used. Definitely there we can at this moment cannot find a clear correlation between these parameters, but we can say that transition of polysaccharide and protein from one layer to another is happening due to the response of the microorganisms to the change in the environmental acidic conditions at the moment. Concerning the treatment with the citric acid, this treatment also contributed to the increase in polysaccharide content. Also, there is some exception, as you can see. Citric acid treatment reduced protein content in soluble white Epps. However, at higher concentration of citric acid, we have increase in protein content in loosely bound Epps as well as in tightly bound Epps. So with increasing citric acid concentration, tightly bound Epps layer damages, which is transformed to the loosely bound Epps layer and soluble organic matter. So we have definitely degradation using those two acids, but we can say that it's more that the greater performance is at the when we use acetic acid. Concerning pharmaceuticals degradation, these are results of our colleagues. We got this heat map, and we can say that we have also this legend that say that most of this heat map is green, so that means that most molecules are present below 10 nanograms per liter on average, and they identified 31 pharmaceuticals. The most molecules are below 10 nanograms per grams on average. So, for example, acetaminophen, atenolone, amoxicillin, ketoprofen, naproxen, etc. Some molecules were not detected. And other specific molecules are presented in various concentration between 20 and 70 nanograms per gram, such as diclofenac, or around 100 nanograms per gram, such as tramadol penicillin. Also, we have exhibited various concentration depending on the samples. We have imopramid showed concentration between 30 and 900 nanograms per grams, with an average around 200. Also, ciprofloxacin reached 13,000 nanograms per grams in one specific sample, and also ibuprofen was the most concentrated pharmaceuticals in most of the samples, reaching concentration up to 11 micrograms per gram. And the concentration in sludge can be related to several factors. Definitely is the occurrence in raw wastewater in the dissolved or in solid phase. Also, it depends on the consumption rate by the population and extraction in urine feces. Also, their presence also is related to the hydrophobicity of the molecules, governing their partition in the particular phase through the sorption in the sludge. Also, it is affected by the removal process by anaerobic digestion. And high concentration of ibuprofen, tramadol, and penicillin can be related also to their high hydrophobicity. On the other hand, we have acetaminophen or sulfamethoxazole having lower log P, which can explain their lower presence in sludge sample despite their high consumption. And large biodegradability of some molecules can be also explained by their low concentration in sludge because of their degradation either in biological treatment of wastewater or in the sludge treatment. And I will conclude that both acetic acid and citric acid pretreatment are promising non-invasive acids for enhanced biogas production, and also we have showed that there is a degradation of organic matter and definitely a removal of and degradation of pharmaceuticals. Thank you for your attention. I'm free for questions and answers. Okay. Quick. Ali pitanja?
Hvala, Anita. Da, ako ima pitanja, slobodno.
Sad